Okay, good morning, everybody. Hope you can hear me. We're going to start now this session, which is on deep by-inspired algorithm. So thanks for being here. We have three papers in this session. We're going to try to stick to the schedule that we have, so that the people can go from one presentation to another in different sessions. So we are going to start with our first presentation, which is already on screen, whose title is Evolving Instinctive Behaviour in Resource-Constrained Autonomous Agents Using Grammatical Evolution. Will be presented by Ahmed Hallawa. So please, Ahmed, you can.
Okay, good morning, everyone. Thank you very much for your attendance. Your presence is really appreciated given the current situation, and special thanks to all the organizers for EvoStar in general and for this session particularly for all the work that they have put to make this work and remotely in these conditions. So I would like to start off with the motivation behind our work. So generally we are dealing with miniaturized autonomous sensory agents. The reason is that they can offer a wide range of applications, such as exploration of unknown environments. This could be looking for resources such as oil and gas. This could be exploring an environment for finding a particular physical features such as leakage, pollution sources, and so on. And in these kinds of environments, the environment is usually GPS denied. We have little information about, usually also very big. So it's very hard to access it. And you will need to use a swarm of agents. And these agents have to be also very small in order to adequately explore the environment. So they are usually limited in hardware resources because they are too small. And they have to operate for longer periods of time because the environment is big. And what makes things even more challenging is that the environment is dynamically changing, and it is hard at the design time to predict what kind of conditions these agents will see. And yet, given all this, we need to have an adaptive behavior to use in an optimal way or close to optimal way the limited resources available on their hardware. So if we try to decompose this problem further, we will find out that the one challenge is that the parameters we are trying to tune, which is on the hardware level of the sensors, and the objectives we want to achieve when exploring these environments, there is no mathematical formalization, or it's very hard to have a mathematical formalization. There are a lot of unknowns. Usually in the loop, there is fluid dynamics, which includes very complex mathematics. So it's very hard to use the typical optimization techniques, and thus a meta-heuristic algorithm such as evolutionary algorithm would be suited to this problem, and that's what we are using. The second challenge is that we have a huge solution space between these low-level parameters, which are usually on the sensor level, and the high-level objectives, which are very abstract, finding leakage or something like this. And for this, we adopted a scheme that we presented 2 years ago, also in EvoStar, Instinctive Evolution scheme. And in this work, we are adapting the scheme as well in our methodology. The third point is a representation of these agents' behavior. So when we studied the use of artificial neural networks, we were challenged by the fact that they are kind of a black box. It's very hard to interpret their output. And also in terms of modularity, there were some challenges there. Finite state machines suffer from a state explosion after a certain point when the behavior becomes complex. And for this reason, we adapted behavior trees, which are modular and reusable, and also can be interpreted in an easier way than artificial neural networks. And also this is the methodology we adapted in this work. But the main focus of our work, so we're using evolutionary algorithms, we inherited Instinctive Evolution scheme, we are using behavior trees, but what we try to solve particularly in this work is how to conduct the evolution of those behavior tree within the context of the Instinctive Evolution scheme that we presented before. And for this, we are using grammatical evolution. And in the coming slides, I'll try to present how this is done. So first, I will have a quick introduction about behavior trees, the instinctive evolution scheme that we are adapting, grammatical evolution, and then I'll explain the methodology we used and show some results and conclude my talk. So behavior trees are basically mathematical model for plan execution. They are hierarchical. From the mathematical point of view, they are a cyclic graph with priorities on the left node. So each node in this tree can return one of 3 possible states. It's success, failure, or running. And you have 2 big classes of nodes which are possible. So you have composite nodes, which are basically a control of the flow of the execution. It could be something like a sequence. So whenever a node returns true, then it checks the other node. It could be parallel, so checking 2 nodes at the same time. So, and there are a lot of possibilities there. And you have execution nodes, which are actually the things that the agent is going to do. So it's either a condition the agent is going to check, or an action the agent is going to do. And of course, you have the root node, which makes sure that all nodes are being ticked in a periodic manner. So on the right side now, we have just a simple example about the behavior of an animal. So in the beginning, the animal checks if there is a predator present or not. So in this case, there was no predator. So then this goes up as to the parent node, which is a sequence. And since it's a sequence, it will not allow checking the other node because the first one returned a failure. Then it goes to the root and then back to the furthest left unchecked one, which is checking hungry or not. In this particular case, the agent was not hungry, so it goes up. And then there is a selector. Selector allows checking the next node, even if the first one is a failure. So it checks this. In this case, it's already true. Then this returns true. And then the agent looks for resources, food and water, because it's an or. So we could not know whether it's hungry or thirsty. So generally, it will look for food resources. And then when this is done, then it goes up and it can rest. Please note that since it's a left first priority, the most important behaviors can be done on the left side. So checking for predator is more important than checking whether the case is hungry or not, and definitely is more important than having rest. And this property is very good to use in our case. Now come to the instinctive evolution scheme that we are adopting in this work. The main idea of this is that we say, okay, the solution space is big, so we want to decrease or limit the solution space a little bit. To do that, we introduce the concept of pools. So we say, okay, the behavior tree has 3 main types of nodes. So you have the actions that the agent can do, the conditions the agents can need to check, and the control nodes, which are the ones that is controlling the flow. So if we could limit the possible actions and put them within this pool and a set of conditions in a conditions pool, then we will have a limited solution space so that in step 6, the evolutionary part works fine. So this is a typical evolution scheme, but we limited the solution space. Instead of working on very high or big solution space, high dimensional solution space, it's a little bit limited. To conduct this limitation, we start off from step 1 by the hardware. We decompose the hardware to different layers. So configuration layers are the things that can be tuned. So it could be in communication, for example, tuning the range, the sensor rate, stuff like that. We have the perception layer, which is the one that is interacting with the environment. So different sensors and their properties. And then we do an optimization based on what we call intermediate objectives. So not the big objective like finding the leakage or so on. We just do one step of optimization on a lower level, on a module level, to try to find the Pareto front and pick from these Pareto fronts the action to introduce in the pool. So now the pool becomes a more limited solutions from the solution space, which we know that they already satisfy some intermediate objectives. And in case of the conditions, we have we check statistically what are the most likely conditions that would be needed to be checked from simulations and from knowledge information. Now the question is, assuming that you have these pools, so all these things are done, how can you now be able to evolve behavior trees given these pools? And this is what brings us to grammatical evolution. So basically, it's one of the, falls under the umbrella of evolutionary algorithms, but they are capable of programming arbitrary language. So we use context-free grammar to map variable length binary strings to syntactically correct programs. So the phenotype can be anything that we define, and you have, like, for example, a binary, and this goes through the grammar and produces a color if needed. In our case, it actually produces a behavior tree. And now we need to design this grammar to fit in the instinctive evolution scheme so that we can use it for behavioral evolution. So the objective, you have three pools: condition pool, nodes pool, action pool, and then this goes to the grammatical evolution and produces behavior tree. In one further step, behavior tree needs to be represented in the hardware. So we also need to have an instruction set that is hardware friendly and can go on to be used in the hardware. So for the grammar, we identified arbitrary behavior tree based on the following alphabet. So you have A for conditions, you have A for action, C for conditions. You have different controls. We use only two that were presented in the previous example. We use some brackets to try to make it easier for the parsing process. We used one node, and this is we added for controlling the position where the crossover takes place. And we have the numbers because numbers are needed to pick which action or condition from the pool. So the identity of which action to be used. So on the left side, you get to see one behavior tree. On the right, you would see, using our alphabet, how would this behavior tree be represented. Then we needed to have some production rules. So basically on the right, you see 4 general ones. So you have the T, which represents the tree, which can be only an action, a condition, and then you could also have other trees. So this allows to the expansion of the expression. Then you have N, stands for nodes. This is the control nodes. In this case, we only use 2, but we can expand this. This is no problem. And then you have the action and the condition, which is basically the numbers, a number identifier based on the position in the condition and action pools. So then, with the presence of the custom crossover operator, this allows us to have a more controlled behavior in terms of crossover. You can do direct insertions of actions and condition because you can expand the pool easily and the grammar should work. We have also done some repair mechanisms, but this is out of the focus of this presentation because of the time reasons. But we added a small repair mechanism in case the tree is not valid. So how to correct this instead of removing it from the pool. And finally, a parser that would take the output and put it in a form of an instruction set. Of course, ideally, we would, if we want to test this evolution loop, then we would like to put the agents in a particular environment and then have this environment be dynamic. So in one case, some increase in velocity, change in pressure, change in temperature, and so on. But the problem is, if we want to see if this algorithm is converging to optimum solution, we don't know the optimal solution if we introduce such a complex environment. So what we did is that we said, okay, what we want is that the agent behave differently in different zones. So we then expose these agents to these zones. So we say, okay, we are going to expose this agent sensors to a particular set of readings, and in each reading there is a zone definition, and we will check for each zone which action was executed by the agent. And we will have like a score list. So if the agent conducted for the particular zone the best action, we identify this best action, what is it? Then we say, okay, it got the optimal score. Anything different, we have gradual scoring for the rest of the actions. So then we can see if we are getting closer to the optimal action for each condition, for each zone or not. And this makes the decision more deterministic, and we will get us knowledge about what is actually going on from the algorithmic point of view to prepare it for real-world implementations. So the fitness function has 2 parts. The first part is how far the action that is supposed to be done from the actions that has actually been executed. The second part is actually inspired by literature. So in literature, there is the suggestion that if you push a little bit of in the fitness function to decrease the complexity of the behavior tree, this will help the evolutionary process to converge faster. That's exactly what we did. So we had a score representing the complexity of the tree relative to the maximum possible nodes. And we say, okay, we try to decrease the complexity as much as possible within the fitness, and this had a positive effect on the overall performance of the algorithm. So then I will show some results. So the first test was that we said, okay, the agent will have 6 sensors and we will expose it to 4 zones. We tried to make the problem challenging, so we made 2 of the sensors not important to detect the zones, so just to confuse the agent. And we also made different possibilities that the agent need to check, for example, from zone 1 to zone 2, sensor 1 is not changing, but if you go to zone 3, it changes. So then it makes the problem a little bit challenging to see how good is the algorithm. This is the results from the first problem or test case. So you have on the x-axis the iterations, and on the y-axis the percentage of correct identification of the zone, thus doing the correct action, so the top score. And as you see, it converges to the optimal solution. What is interesting, also looking at the complexity changes and the complexity dynamics, that the agents are in the population exploring different possibilities and finally converging to one possibility, which is leading to the optimal case. Afterwards, we wanted to test how this scales up. So we tried it for 8 agents and 8 zones, making the problem a little bit more hard. Again, there is convergence. It didn't reach the optimal 100%. It reaches actually 94%. But the same behavior, you get to see that there are conversions and also an exploration of the complexity of the behavior tree is done on to ensure that this is converging towards the optimal behavior. So now to conclude my talk. So in this paper, basically, we introduced a grammar capable for evolving behavior trees that is workable within the context of the Instinctive Evolution scheme. We introduced in this grammar particular cases to handle custom crossover operations, and also to allow the incorporation of domain knowledge, because you can simply add to the pools any number of actions and conditions, and the same grammar could work. You don't need to do any changes. We also implemented a repair mechanism and a parser to ensure that the execution of the algorithm is adequate and usable on the hardware. And we found out that the optimal actions where the algorithm converged to them, and in many cases it required lower complex behavior trees, and that the convergence is relatively fast, and there is a good balance between the exploration and the exploitation. Obviously, for future work, we would like to extend the simulation environment to use one. Actually, we already have done a lot of work in this direction to use ROS and to include more realistic fluid simulations. And early results are showing very optimistic output. And then finally, the integration of this on the hardware, because our objective is to use the output from the algorithm on a real hardware and test it on a real environment. And with this, I would like to conclude my talk, and I will be happy to answer any of your questions. Thank you very much.
So thanks. You are now receiving the virtual applause from all attendees. And
hello?
Thanks. Yes, can you hear me? Yeah. So thanks for the very interesting presentation, and thanks also for being on time. I think that we have a couple of questions on the room. So I'm going to maybe let people ask themselves those questions. So I have one question by Federico Divina. Please, Federico, go ahead.
Hi, Ahmed.
Hi, Federico.
How are you?
I'm good.
Just a quick question, because I'm kind of familiar with this project.
Yeah.
So, so on in slide 6, I think you say that you pick a solution from the Pareto front, and I wanted to ask you how you select the solution from the Pareto front.
So, so basically what we do is we divide the hardware into different subsystems. So let's say communication system, we will have the objective of improving the signal to noise ratio while decreasing the information loss. And then on the communication, let's say you have the range of communication, the rate you conduct communication as 2 variables. So this becomes like a 2 objective optimization problem. We use typical algorithms, something okay like NSGA2, for example, in this particular case, because we have 2 objectives. Maybe for more, we think about other solutions. And then we conduct the optimization and we try to find out the Pareto front. We can, in advance, based on the population, pick the number of solutions that we want. Let's say we want to have 30 solutions to be put on the action pool. So then we say, okay, we do this optimization for the 30 solutions, and then we take these, so we conduct some optimization, and then we pick those and put them in the action pool. And the idea is that when we do this, we get rid of other solutions that are not of interest to us because they do not, they are suboptimal and they are not necessary to explore because they are defying some intermediate objectives anyway. So why should we let the EA part on step 6 explore them?
Okay, thank you.
No, thanks.
Thank you for your talk.
Yeah, thank you.
Thank you for the question. There are a couple of other questions. I'm going to make them directly for the attendees. So one question is about what tools you have used for the simulation and what library for grammatical evolution. And another question is what kind of hardware are you planning to use this on?
So for the simulations, in the first ones we used MATLAB. So we didn't do something because this was a controlled environment. We then afterwards moved to ROS. And from ROS, we used the underwater simulation libraries available there to simulate the behavior of the agents in pipes and have an intermediate, so not very accurate fluid simulation, but not also very generic one. So these are the 2 important tools we used. The second question regarding the hardware. So in this project, we actually developed our own hardware. So it was because energy is very important for us. So our teams in Leuven and Eindhoven were working on an ASIC design so that it's actually for the first time it would be a fully evolved hardware. So no processor, just this behavior, and it will be the first hardware behavior-driven hardware put on an agent for these purposes. So we built this in-house with cooperation with the University of Leuven and the University of Eindhoven.
Okay, great. Thanks. Thanks for the answers. And I see that one more question. I think that we are a little short of time. So if you could just answer it very briefly, there's a question that is: have you considered doing the evolution in real robots? If so, how would you handle the evaluation with different initial conditions?
That's a very good question. In this project, we try to conduct these evolution. So we do some statistical analysis to try to converge with some certainty about the performance of this algorithm. So we tackle these different initializations by statistical means, basically, to try different initialization seeds and ensure that our algorithm can handle, so the performance is not deteriorating with a big range given the situation we have. But of course, I mean, this is a very complex topic. I mean, we can also take this discussion. I'll be happy to talk about this in more details offline. And my information is also available on the website, and we have also a project called Phoenix. It's an European Horizon 2020 project, and I'll be happy to answer any of these questions offline if I'm not super detailed due to time constraint.
Okay, thank you. So yeah, thank you for the very interesting presentation and also for the very enlightening answer. So thank you for having the applause from the room.